Section 3.5, Deployment Pipeline, Build and Test. Continuous delivery is a holistic approach for quickly, reliably, and safely delivering high-quality software, as I explained in Chapter 1. The primary pattern for adopting such an approach is the deployment pipeline, which goes from code commit to releasable software. It should be automated as much as possible, and it should represent the only path to production. Based on the concepts described by Jez Humble and Dave Farley in their Continuous Delivery book, Addison Wesley Professional 2010, and by Dave Farley in his Continuous Delivery Pipelines book, 2021, we can identify a few key stages in a deployment pipeline. Commit stage. After a developer commits new code to the mainline, this stage goes through build, unit tests, integration tests, static code analysis, and packaging. At the end of this stage, an executable application artifact is published to an artifact repository. It is a release candidate. For example, it can be a jar artifact published to a Maven repository or a container image published to a container registry. This stage supports the continuous integration practice. It's supposed to be fast, possibly under 5 minutes, to provide developers with fast feedback about their changes and allow them to move on to the next task. Acceptance stage. The publication of a new release candidate to the artifact repository triggers this stage, which consists of deploying the application to production-like environments and running additional tests to increase the confidence about its releasability. The tests that run in the acceptance stage are usually slow, but we should strive to keep the whole deployment pipeline execution to under 1 hour. Examples of tests included in this stage are functional acceptance tests and non-functional acceptance tests, such as performance tests, security tests, and compliance tests. If necessary, this stage can also include manual tasks like exploratory and usability tests. At the end of this stage, the release candidate is ready to be deployed to production at any time. If we are still not confident about it, this stage is missing some tests. Production stage. After a release candidate has gone through the commit and acceptance stages, we are confident enough to deploy it to production. This stage is triggered manually or automatically, depending on whether the organization has decided to adopt a continuous deployment practice. The new release candidate is deployed to a production environment using the same deployment scripts employed and tested in the acceptance stage. Optionally, some final automated tests can be run to verify that the deployment was successful. This section will guide you through bootstrapping a deployment pipeline for catalog service and defining the first steps in the commit stage. Then I'll show you how to automate those steps using GitHub Actions. Section 3.5.1. Understanding the commit stage of the deployment pipeline. Continuous integration is a foundational practice of continuous delivery. When adopted successfully, developers work in small steps and commit to the mainline, the main branch, multiple times a day. After each code commit, the commit stage of the deployment pipeline takes care of building and testing the application with the new changes. This stage should be fast, because a developer will wait until it completes successfully before moving on to their next task. That's a critical point. If the commit stage fails, the developer responsible for it should immediately deliver a fix or revert their changes so as not to leave the mainline in a broken state and prevent all other developers from integrating their code. Let's start designing a deployment pipeline for a cloud-native application like Catalog Service. For now, we'll focus on the first few steps in the commit stage, Figure 3.8.
Figure 3.8. The first part of the commit stage in a deployment pipeline.
After a developer pushes new code to the mainline, the commit stage starts by checking out the source code from the repository. The starting point is always a commit to the main branch. Following continuous integration practices, we'll aim to work in small steps and integrate our changes with the main branch multiple times a day, continuously. Next, the pipeline can perform several types of static code analysis. For this example, we'll focus on vulnerability scanning. In a real-world project, you would probably want to include additional steps, such as running static code analysis to identify security issues and check compliance with specific coding standards, code linting. Finally, the pipeline builds the application and runs automated tests. In the commit stage, we include technically focused tests that don't require deploying the entire application. These are unit tests and often integration tests. If the integration tests take too long, it's better to move them to the acceptance stage to keep the commit stage fast. The vulnerability scanner we'll use in the Polar Bookshop project is Gripe, see this link, a powerful open-source tool that's increasingly used in the cloud-native world. For example, it's part of the supply chain security solution provided by the VMware Tanzu application platform. You can find instructions on how to install it in Section A.4 of Appendix A. Let's see how Gripe works. Open a terminal window, navigate to the root folder of your catalog service project, catalog service, and build the application with /gradle build. Then use Gripe to scan your Java codebase for vulnerabilities. The tool will download a list of known vulnerabilities, a vulnerability database, and scan your project against them. The scanning happens locally on your machine, which means none of your files or artifacts is sent to an external service. That makes it a good fit for more regulated environments or air-gapped scenarios.
See this code.
Note: remember that security is not a static property of a system. At the time of writing, the dependencies used by Catalog Service have no known vulnerabilities, but that doesn't mean this will be true forever. You should scan your projects continuously and apply security patches as soon as they are released to fix newly discovered vulnerabilities. Chapters 6 and 7 will cover the remaining steps in the commit stage. For now, let's see how we can automate a deployment pipeline with GitHub Actions. That's the subject of the following section. Section 3.5.2, Implementing the Commit Stage with GitHub Actions. When it comes to automating deployment pipelines, there are many solutions from which you can choose. In this book, I'm going to use GitHub Actions. See this link. It's a managed solution. It provides all the features we need for our project, and it's conveniently already configured for all GitHub repositories. I'm introducing this topic early in this book so that you can use the deployment pipeline to verify your changes while working on the project throughout the book. Note: in the cloud-native ecosystem, Tekton.dev, is a popular choice for defining deployment pipelines and other software workflows. It's an open-source and Kubernetes-native solution hosted at the Continuous Delivery Foundation, CD.Foundation. It runs directly on a cluster and lets you declare pipelines and tasks as Kubernetes custom resources. GitHub Actions is a platform built into GitHub that lets you automate software workflows directly from your code repositories. A workflow is an automated process. We'll use workflows to model the commit stage of our deployment pipeline. Each workflow listens to specific events that trigger its execution. Workflows should be defined in a .github workflows folder in a GitHub repository root, and they should be described following the YAML format provided by GitHub Actions. In your catalog service project, catalog service, create a commitstage.yml file under a new .github workflows folder. This workflow will be triggered whenever new code is pushed to the repository.
Listing 3.20, Defining a workflow name and trigger.
Each workflow is organized into jobs that run in parallel. For now, we'll define a single job to collect the steps described previously in Figure 3.8. Each job is executed on a runner instance, which is a server provided by GitHub. You can choose between Ubuntu, Windows, and Mac OS. For Catalog Service, we'll run everything on Ubuntu runners provided by GitHub. We'll also want to be specific regarding which permissions each job should have. The build and test job will need read access to the Git repository and write access to the security events when submitting a vulnerability report to GitHub.
Listing 3.21, Configuring a job for building and testing the application.
Each job is composed of steps which are executed sequentially. A step could be either a shell command or an action. Actions are custom applications used to perform complex tasks in a more structured and reproducible way. For example, you could have actions for packaging an application into an executable, running tests, creating a container image, or pushing an image to a container registry. The GitHub organization provides a basic set of actions, but there's also a marketplace with many more actions developed by the community. Warning: when using actions from the GitHub marketplace, handle them like any other third-party application and manage the security risks accordingly. Prefer using trusted actions provided by GitHub or verified organizations over other third-party options. Let's complete this first part of the commit stage by describing what steps the build and test job should run. The final result is shown in the following listing.
Listing 3.22. Implementing the steps to build and test the application.
Warning: the action that uploads the vulnerability report requires the GitHub repository to be public. It works for private repositories only if you have an enterprise subscription. If you prefer keeping your repository private, you'll need to skip the upload vulnerability report step. Throughout the book, I'll assume all the repositories we create on GitHub for the Polar Bookshop project are public. After completing the declaration of the initial commit stage for the deployment pipeline, commit your changes and push them to the remote GitHub repository. The newly created workflow will be immediately triggered. You can see the execution results on your GitHub repository page on the Actions tab. Figure 3.9 shows an example of the results after running the workflow in listing 3.22. By keeping the result of the commit stage green, you can be quite sure that you haven't broken anything or introduced new regressions, assuming that you have proper tests in place.
Figure 3.9. The commit stage workflow is executed after you push new changes to the remote repository.
The step for running the vulnerability scan is based on an action provided by Anchor, the company behind Gripe. In listing 3.22, we do not fail the workflow if serious vulnerabilities are discovered. However, you can find the scanning results in the security section of your Catalog Service GitHub repository. At the time of writing, there is no high or critical vulnerability in the Catalog Service project, but things might be different in the future. If that's the case, consider using the latest available security patches for the affected dependencies. For the sake of the example, and because I don't want to disrupt your learning journey, I decided not to make the build fail on finding vulnerabilities. In a real-world scenario, however, I recommend you configure and tune Gripe carefully and according to your company policies regarding supply chain security, and make the workflow fail if the result is not compliant, setting the fail build property to true. For more information, refer to the official Gripe documentation. See this link. After scanning the Java project for vulnerabilities, we also included a step to fetch the security report generated by Gripe and upload it to GitHub, independently of whether the build succeeds or not. If any security vulnerability is found, you can see the results in the Security tab of your GitHub repository page, Figure 3.10.
Figure 3.10. A security vulnerability report generated by Gripe and published to GitHub.
Note: at the time of writing, Gripe doesn't find any vulnerabilities in the codebase provided with this book. To show you an example of a vulnerability report, Figure 3.10 shows the results of Gripe scanning a different version of the project, purposely full of known vulnerabilities. That's it for this chapter. Next, I'll cover one of the main cloud-native development practices: externalized configuration.